Welcome back to another explainer. Okay, let's dive right into this. Today, we're looking past the steel beams and the concrete walls to explore the hidden science sitting literally right beneath the lowest floor, geotechnical engineering. We're going to be unpacking the rigorous U.S. Army Corps of Engineers manual on soil-bearing capacity and foundations. It's this absolutely fascinating world where some very subtle math prevents, well, catastrophic failures.
Here's our roadmap for today. We'll start with why buildings don't sink, then move into understanding soil-bearing capacity, how foundation soils fail, shallow foundations, and finally, deep foundations. Don't worry, we're going to build this complex engineering logic from the ground up, starting with just basic soil behavior.
Section 1. Why buildings don't sink, or the hidden forces beneath our feet. Think about it. We place immense, mind-boggling weight onto simple dirt and rock. So how does a massive skyscraper avoid sinking straight into the mud? Gravity is constantly pulling the building down, right? So the Earth actually has to push back with an equal force just to maintain stability. And this battle, this push and pull, is the fundamental problem and solution framework of literally all foundation engineering. Historically, humanity relied on pretty basic stuff. Simple earth-fast wooden posts, trenches filled with rubble, or basic pad stones. But, as our buildings grew heavier and vastly more complex, we really had to adapt. Modern foundations utilize highly engineered concrete slabs on grade, massive impact-driven piles, and these deep-drilled shafts to completely bypass weak surface mud and transfer all that weight down to stronger subsoils.
Section 2. Understanding soil-bearing capacity, the math that holds us up.
Now, what's really interesting here is that before a single drop of concrete is ever poured, engineers look at one absolute core metric: bearing capacity. By definition, this is the ability of soil to safely carry the pressure placed upon it without undergoing a shear failure and the large settlements that come with it. It's actually not just about keeping the building upright, it's equally about keeping the ground from shifting unevenly underneath it. To do this, the USACE manual outlines a highly specific formal procedure. Step 1. Evaluate the ultimate bearing capacity. Basically, what is the absolute maximum pressure the soil can take before it outright fails? Step 2. Determine a factor of safety. Step 3. Calculate the allowable bearing capacity. You do that by dividing the ultimate capacity by that factor of safety. And Step 4. Perform a settlement analysis. This rigorous step-by-step logic is exactly how engineers mathematically predict the unpredictable behavior of the Earth. Let's actually look a little closer at that factor of safety, or FS. Engineers essentially build in a mathematical buffer to protect lives and property. And that required buffer, it changes depending on what you're building. For instance, a regular silo or warehouse might have a factor of safety of 2.5, but a railway bridge, that requires a factor of safety of 4. That means the soil must be calculated to hold 4 times the actual applied load. Why? Because the dynamic, vibrating, pounding of heavy trains, plus the unthinkable consequences of a failure, demand a much, much higher margin of error. Section 3. How foundation soils fail. When the ground gives way. Because to build safely, we really have to understand exactly how the literal dirt beneath us can fail. And soil behaves very differently depending on what it's made of. Engineers broadly classify them into cohesive and cohesion-less soils. Cohesive soils, think clays and silts, have particles that actually bond together. They hold their shape, but they are super prone to shrinking and swelling when water gets introduced. On the flip side, cohesion-less soils, like sands and gravels, get their strength purely from the internal friction of particles rubbing together when they're confined. Engineers must meticulously identify these early on because, as you can imagine, a foundation pushing down on sand is going to get a completely different kind of pushback than one resting on wet clay. And when the load is simply too great, those soils fail in some pretty dramatic ways. A general shear failure is a sudden, often catastrophic collapse where the soil literally shears sideways. This causes the ground surface to visibly bulge upward and the whole structure to tilt violently. On the other hand, a punching shear failure is a sudden vertical settlement straight down into the earth. It's really common in loose sands, and honestly, the terrifying part is that there are often no visible slip lines or warning bulges at the surface. The building just drops. But here is a fascinating reality check taken directly from the USCE manual. Ultimate shear failure is seldom a controlling factor in design because few structures are able to tolerate the rather large deformations that occur in soil prior to failure.
Basically, long before a building completely tips over, small, uneven settlements will cause massive internal distortions. Walls will crack, doors will jam, sensitive machinery will fall totally out of alignment. And that right there is why the settlement analysis we talked about earlier is almost always the true limiting factor in foundation design.
Section 4. Shallow foundations. Spreading loads and staying close to the surface. Now that we understand the problem of soil failure, let's look at the solutions. A shallow foundation is placed within a depth beneath the ground surface that is less than the minimum width of the foundation itself. It essentially uses a wide footprint to distribute heavy loads over a much larger area. It's exactly like how a pair of snowshoes keeps you from sinking into deep snow. Engineers have a whole toolbox of these shallow foundations. We've got spread footings that distribute the load of isolated individual columns. We have continuous and wall footings that support long, load-bearing walls. And for incredibly heavy structures, or when you're forced to build on notoriously soft soils, we use mats. Mats are essentially these massive, continuous concrete slabs that span the entire footprint of the building. They act almost like giant concrete rafts just floating on top of unstable soil to prevent that uneven settling. Ensuring these shallow foundations actually work relies heavily on the mathematics of spreading. Engineers don't just guess here. They rely on incredibly complex theoretical models, like the Terzaghi, Meyerhoff, Hansen, and Vasek general equations. Now, we aren't going to get bogged down in the heavy algebra today, but just know that they are precisely calculating variables like the foundation's width, the cohesion of the soil, the weight of the dirt and the failure wedge, and any surcharge pressures, all to guarantee the ground will hold firm. Section 5. Deep foundations. Reaching down and bypassing the weak layers. So let's move on and see how this builds when the surface soil is simply too weak to trust with a shallow footprint. In those cases, engineers are forced to abandon the surface and plunge deep into the earth. This happens for a few specific triggers. Maybe the shallow strata just lack bearing capacity, or there's a serious danger of excessive surface settlement. Or the structure might need to resist massive lateral forces from wind or earthquakes. They might also need to fight upward uplift forces from expansive, swelling clay, or they need downward protection against the soil naturally eroding and washing away in riverbed scour. Basically, when the surface fails us, we go deep. The two main ways we execute this are with drilled shafts and driven piles, and there is a sharp contrast between them. Drilled shafts are created by gently boring a dry or slurry-filled hole and then filling it with reinforced concrete. This causes almost no ground heave and minimal vibration to any surrounding structures. In sharp contrast, driven piles involve violently hammering a solid displacement pile directly into the earth. And while driving piles can cause the ground to heave up in clays, it wonderfully densifies loose sands through the sheer, brute force of the impact. Once they're installed, these deep foundations utilize a brilliant two-part harmony to transfer the load safely into the earth. The total capacity relies on base resistance, where the very tip of the pile bears down hard against rock or dense soil, combined with soil shaft side friction. That side friction is generated along the entire vertical length of the buried cylinder, gripping the surrounding soil almost like friction tape. Working together, they hold up massive, unimaginable structural loads. So, I want to leave you with this provocative thought to chew on. As you sit there right now, what invisible engineering and complex soil mechanics are actively working directly beneath your feet to keep you from sinking into the earth? It really is a profound testament to the power of structured engineering. Thank you so much for joining me to explore the silent, hidden math keeping our world upright. Keep learning, stay curious, and I'll see you in the next explainer.